Okay, last talk today. Okay, the idea is that we've now sort of walked through particle generation to creation, photon propagation, and then detection at the PMTs and the subsequent digitization of the PMT pulses. So what this talk will be on is the processors that achieve some of this. Specifically, there's event processor structure that are intended to manipulate the information in the events. And I'll try and walk through the structure of those processors, talk about what exists as a processor right now, and talk about how to write a processor. So an event processor in RAT is part of the event loop. It doesn't create new events. That's up to the generators to create the events, but it receives the events one at a time and can do things like change information in the event by adding or altering its contents. It can also just passively observe the event and look at information, maybe print something to the screen or something like that. And yeah, just to highlight, a processor is not a producer or a generator. The event producers are the things that are actually creating the events. These processors are manipulating information about the events. So we're going to go into a lot of detail in the various processors that exist. The simplest processor that is on almost every example macro is called the count processor. It literally just counts the number of simulated events and prints that to the screen. So if you ran a macro yesterday, you might have seen a printout near the bottom of the screen that just said simulated 10 events with some number of triggered events. That's just the count processor looking at the event information and printing to the screen. So why would you use a processor? Well, it's a framework in RAT that allows you an easy way to loop through the events and extract information about the events. Again, you would do this to manipulate the data structure for event. For example, the dark noise processor that I'll talk about adds additional PMT hits, specifically dark noise hits. You might want to fill the data structure with some new information. For example, if you have a reconstruction algorithm, those are written as processors. Those will take in some information about the event and then want to write to the data structure some reconstructed quantities like the fitted time and position of the particles. You might use a processor to launch new processing. That's a typical example of this is the data acquisition system that decides whether the detector triggered and whether that trigger should cause additional things to occur. Processor might provide a helpful tool. Some examples of that are, as I mentioned, a count processor just counts events, points to the screen. And there's a processor called the prune processor that removes branches of the data structure to try and shrink the file size. And again, all the processors, the intention is that they're very easy to call from the RAT macro, as I'll show. And this is just a brief aside, but I think it's important to point out that processors work over both data and simulation. So for the vast majority of this entire workshop, we're talking about simulation. But for example, in SNOW+ and EOS, we read in our data into RAT and process it using the exact same set of processors, minus a couple, that we run on the simulation. So we have literally the exact same set of code running on our data as we do on the simulation. Okay, so maybe we can get into just an example macro that we'll come back to a couple times. So again, we saw in Garrett's talk yesterday how the control flow in a macro works. And we saw specifically this processor block that starts the line run initialize that freezes the loading of parameters and then lets you set up the processors that you want to run. These processors run in the order specified in the macro. And the final processor is specified by the proc last command, although you don't need that command. You can use rat proc as well. Typically, the last processor is the processor that's writing out the data. So here, that processor is called out and tuple. Again, as we mentioned several times, we're going to be talking a lot about that tomorrow. So yeah, this is just to continue to remind people that you can manipulate the ratpac-two variables specifically for these processors by either setting ratdb parameters from the macro. So for example, I'm showing an example here where you're adjusting something about the PMT noise processor. And you can also manipulate processors using this rat proc set update. This rat proc set command. In this case, the count processor takes as input an optional proc set which sets a value in the processor called update, which just tells the processor how often to print the number of events to the screen. So whether a variable can be set using the proc-set command should either be documented on the web page, or you can look at the source code. There's no a priori way to know whether you can use the proc-set to set a variable, other than look at the documentation or the code. And yeah, I just want to highlight that again. So there's the user guide for processors is one of the more developed parts of the documentation. And there's also a programmer's guide. So at the end of this talk, I'll be talking about how to write a processor. There is a reasonable level of documentation for that as well. So if you're interested in writing a processor, that should be helpful. So I'm going to basically go through the list of all the processors in ratpac in some level of detail. So there are PMT related processors, data acquisition related processors, waveform processors. And again, some of this will repeat what James has already talked about. Then I mentioned the count processor, the prune processor, and there's something called the Python processor that I'll cover in just a tiny bit of detail. We're going to hear all about reconstruction at the beginning of tomorrow. So those are also implemented as processors. And we will also hear about the output processors tomorrow. And so I'll save those two for tomorrow's talks. Okay, so as I mentioned, the simplest processor in ratpac-two, and it actually provides a very nice example. If you want to get started writing a new processor, I would recommend starting from the count processor. Just look at that code and see what it's doing, because it provides a nice infrastructure for how you'd write a new processor. So yeah, as I mentioned, it simply counts simulated and triggered events and prints those to the screen. I find this to be a pretty useful diagnostic sometime, particularly if not all of the events are triggering, as you can see in this example from the documentation. In this documentation, the count processor is telling you you've simulated at this point in time, you've simulated 5 events and 3 of them have triggered the detector. And I'll try and show snapshots from the documentation just to remind you that this stuff is fairly reasonably documented, which is hopefully useful. And then it's simple to run from the macro. As people have seen in the example macro, you just run /rat/proc count. And then in the documentation, it tells you what parameters you can set from the macro using the proc-set command. In this case, it's just one variable. Okay. There are then the PMT related processors. So these are processors that allow you to manipulate something about the PMT information. There's 2 of them. The one that I'm going to focus on is the one that adds dark noise to the event structure. There's also one that adds something called after pulsing to the event structure. That one's fairly untested, and I won't get into that one too much. But if you're interested in simulating after pulsing in your detector, that does exist, just relatively untested, might need a bit of tweaking. So the idea of these processors is that you add photoelectrons to the event structure, specifically the MCPMT objects, for photoelectrons that are not generated from the detection of optical photons. So these are different than when light hits the PMT and creates a photoelectron. These are specific processes that generate photoelectrons in different ways. So there are very specific processors that add them to the data structure. And you need to turn on those processors in your macro for them to run. So for example, the noise processor is simply run by setting /rat/proc noise. And there's certain things that you can set from proc-set. For example, the rate of dark noise that you want to simulate in hertz. And again, reminder that almost all the processors can also be manipulated from the ratdb table. In this case, the ratdb table is called noise proc. Again, that should be documented. And there are various parameters that you can change from the ratdb table. And that means if they're in a ratdb table, you can also edit them directly from your macro with the appropriate command. So here you have things like a flag that specifies to rat how you'd like to simulate the dark noise. Some noise rates, some information about the windows and things like that you can read more about in the documentation for this specific processor. Any questions about the dark noise? Okay, moving on to the DAC processors, which are maybe the most important in terms of how the infrastructure for ratpac works. So the idea with the DAC processors is they typically what they do is build up information about the PMT heads from the MC PMTs, and I'm going to give a very specific information about this, a very specific example of this in a second. So they build up information about the PMT hits and then use that information to issue a trigger decision, whether or not the detector triggered. There are several example processors that do this. One's called simple DAC, there's one called force trigger, and one called split EV DAC. We'll get into each of these in a moment. But the idea is these are really simple versions of a data acquisition system that produces a trigger and are intended mostly as placeholders. Any detector that you would build probably have some sort of trigger system. You would need to, if you wanted a realistic trigger simulation, you would have to perhaps build off one of these to implement a realistic trigger for your detector. These can be used, these are very useful for maybe designing a detector where you don't need to worry so much about the details of your trigger system and care about, some downstream information. But once you have some sort of realistic trigger system that you've built, you would want to stop using these examples. Yeah, so this is just to emphasize, I'm going to come back to this several times, next couple of slides. The trigger decision issued by a data acquisition processor is a critical moment in the simulation chain. Once that trigger is issued, if no trigger is issued, let's say for some reason your data acquisition processor decided there shouldn't be a trigger, no detector events will be produced. And by that, I mean any events in the event part of the data structure, of the rat data structure. Go back to Tony's talk. There's the true Monte Carlo part of the data structure, and then the event part of the data structure. And if no trigger is issued, nothing in the event part of the data structure will be filled, and nothing downstream of that event data structure will be filled. All of those things rely on a trigger being issued, basically a signal telling your detector that it should produce that event information. And that includes things like the digitized waveforms that we just heard about. There will be no digitized waveforms produced unless you actually have a trigger. So yeah, I say here, in other words, only the true information about the particle, the produced photons, and the detected light will be saved, and none of the detector specific quantities will get saved unless you have a trigger. So if you want to look at digitized waveforms, for example, you have to make sure that you're running one of these DAC processors.
So detector light means the number of V those at the photocathode.
That would be that would be part of the true information, because you have some true number of detected photoelectrons at the photocathode. So there's something called, James mentioned, the MC photoelectron or something like that. That's a true information. You can get that information regardless of whether or not the detector triggers. It'll be saved to the file. The type of information that would not be saved to the file is like an event number or something like that. Some very specific detector related quantity, a trigger time, any of the digitized waveform information, any information related to processing of the photoelectrons at the front end or something like that. Anything your electronics would basically do would not be saved. Anything up to the photoelectron, including the photoelectron, will be still saved. So yeah, you'll hear this several times in ratpac. We distinguish between the true quantities, we use that word a lot, which is like the true information that occur to the detector, and then the detector quantities, which are everything the electronics would produce by processing the information from a photoelectron. And then, okay, here's an example of why you might really want to run the data acquisition. If you're trying to run a fitter, the fitter's like a reconstruction algorithm that Sam will talk about tomorrow. They typically run on some sort of detector information, some sort of PMT hit time or something like that. And you would need to run a DAC in order to produce that PMT hit time in order to successfully run a reconstruction algorithm. The reconstruction algorithm is not going to run on the total true number of photoelectrons that are detected. Okay, so a couple examples of what two of these DAC processor do. The forced trigger is probably the simplest DAC, and is one that you may use for testing. Basically, what it does is forces the detector to emit a single trigger for every simulated event. So let's say you simulated an electron in your detector, regardless of the number of photoelectrons that are detected or the amount of light produced, you're going to issue a trigger and thus save the waveforms and the other information associated with the PMTs. So this allows you to basically bypass some of these problems that I was just mentioning and just say, okay, I just want a trigger for every single simulated event, and I don't want to worry about realistically simulating a trigger. This also has general use. Maybe your calibration source you've deployed just causes the detector to trigger every time it produces an external signal. It causes the detector to trigger. Then you could use the force trigger to mimic that type of signal. A more realistic type of trigger, again, not specific to any detector, but maybe one that is sort of similar to some that are implemented for some detectors, is called split EV DAC. Basically what it does is for every single PMT hit, creates a little square pulse with a fixed size and width, and then sums all those square pulses together. And then compares the sum of those square pulses to a global trigger threshold. And if that sum of square pulses, you can sort of imagine them summing up in time, crosses a global trigger threshold, then it issues a trigger. This one's nice because it's a bit more realistic. Now your trigger depends on information from the PMTs. It also does things like it has a very specific, and tunable trigger window. So for example, if you're simulating neutrons or inverse beta decay events or something like that, what you'll see is that particles that interact at different times will cause multiple detector events. So you have a single simulation. Let's take inverse beta decay as an example, where you have a positron and then a delayed neutron. The neutron will scatter for a while before being captured and thus be delayed relative to the prompt positron. So in your simulated event, you have one event that includes the truth information for both the neutron and the positron. In the detector event, you have two separate events. One is for the prompt positron, and the second is for the delayed neutron, each of which are separate in time. So you create two detector events. Yeah, I think I have another slide on that, but I just want that can be very confusing when first starting to run event simulations where you have things separate, single simulations where you have things separated in time. So you can pause there and see if there are any questions.
So what if the trigger window is long enough that the both two events are falling?
Yes, that should be fine. So what you'll get, for example, in that case, let's say, you have a microsecond window and they're 500 nanoseconds apart. You'll see the prompt light in the trigger window from the first event, and then the delayed light still in the same trigger window from the next event. If you plot the PMT hit times in a single event window, they won't be separated. So it should handle all of those type of things. Okay. Question. Okay, and like I mentioned, especially the split EV DAC, but the other DACs as well are fairly configurable from the macro. So again, you can change a lot of the features about split EV DAC directly from using these ratpac-two commands. Again, copying this from the documentation, you can go and change things like the trigger window, the trigger threshold, and how the trigger steps through the how it works in some details. Knowing exactly how each of these things affect the simulation either requires reading a little bit of the documentation and maybe some of the source code, but I think some of them are the main ones, like trigger threshold, for example, are fairly well documented, are the ones that you mostly use. And then, yeah, this is repeating myself, but I'll do so anyway, just to be super clear. For events that do trigger the detector, you are going to create these event objects. So this DSEV thing that Tony talked about is the event object. Then all the downstream objects. So then you create these DSPMT objects, and you can optionally create the digitized waveforms, which are called the DS digit objects, and the analysis outputs that are saved in these digit PMT objects. And so I know this is confusing. I'm going to go through each one of these in a bit more detail and specifically spend some time on this last one, the DS digit PMT, which is probably the most useful of these downstream objects because it contains information that you might use in a reconstruction algorithm, for example. And this is, again, I'm repeating myself a little bit, but just noting this thing about the EV branch, which is for a single simulated event, you can have multiple detector events depending on the timing inside of that simulated event. And then there are certain processors, we'll talk about this when writing a processor, that may want to loop over just the MC events, and certain processors that may want to loop over the EV events. And those can be different lengths. So you need to be a little careful when writing a processor to remember this. Okay, and now moving on from that. So that was sort of the idea behind triggering specifically with some sort of data acquisition simulation. And after triggering, you can optionally digitize the PMT pulses. And this is turned on for from dac.ratdb. So I'm showing here a snapshot of the force trigger entry in dac.ratdb. And what you see here is a specification, the digitizer name that you're going to by default use for all of the channels. There's no option to use different types of digitizers for different channels, and whether or not to digitize the channels. And so these are turned on by default, and the V1730 is the default digitizer. As James mentioned, there's only two options right now to digitize on, but what I think are sort of some of the more common cane boards, the V1730 and V1742. And the idea here is that from the dac.ratdb file, you basically turn on the digitization and then specify in your digitizer.ratdb file what that digitization looks like. So you get things like the number of samples, the sampling rate, the dynamic range, and things like that specified in the digitizer file. And this is literally going to go in and digitize the PMT pulses in exactly the same way an oscilloscope or a fast digitizer would do so. Okay, and James showed an example waveform, but again, I'll show another, which is produced a simulated digitized waveform produced from information from the PMT hit times and charges. And the idea here is the simulated digitized waveforms should be indistinguishable from the ones that you're getting out from your detector. They should look exactly like the PMT pulses coming out of your detector. So if you put rat and you plugged it into a scope, it should look like what's coming out of your detector, basically. So anyway, so now that we have these digitized waveforms, the next step would be to extract things from them. This is going to be the next processor that we're going to talk about, which is specifically the waveform processors. And so the things that you would naturally want to extract from these waveforms are the hit time or the arrival time, or maybe some like threshold time, however you want to put it. You want to get the time of this PMT pulse and maybe the PMT charge. So you might integrate this PMT pulse to produce a charge. So those are two common things to extract from these waveforms, and RAT specifically provides processors that extracts that type of information. Okay, so the waveform processing takes place in a couple steps. The first one, and I'll show a full example on the next slide. The first one is called waveform prep. That is a very specific processor that runs, and it basically performs basic analysis that I just described, which is doing things like calculating this baseline and subtracting it in order to integrate the charge. It's calculating a hit time based on the rise time here, those type of things. So it's basically doing a variety of simple calculations to get information about the waveform. That's more higher level than just all of the voltages of all of the samples in the waveform. And then, yeah, this is the important part. So the important part is this higher level information extracted from the waveform analysis is saved to this digit PMT object. So if you're ever writing some reconstruction thing, this digit PMT object contains the information that you might want to use in your reconstruction algorithm. presuming your detector is actually digitizing the waveforms. If your detector is doing electronics or doing something completely different, you would need to, of course, do something different. So this all assumes that your detector is digitizing the waveforms. And yeah, I've sort of mentioned this already too, which is these digit PMT objects are nice because you allows you, again, you can directly compare between data and simulation. All of the same processes that are happening in the electronics should be happening in ratpac. So you can do direct data simulation comparisons by looking at the information in these objects. So yeah, you've simulated the full chain from trigger to waveform digitation to waveform processing. So in addition to the waveform prep processor that I just mentioned, and again, I'm going to give a full example on the next slide. There are more sophisticated waveform analysis processors that can be run. First one is called waveform analysis Gaussian. It just basically fits a Gaussian to, so you can imagine just fitting a Gaussian distribution to this PMT pulse. That is provides a slightly more precise way to extract things like the hit times or maybe perhaps the integrated charges than more simpler algorithms that are provided in the waveform prep processor. So, okay, yeah, okay. Finally, I'm getting to the full example here. Again, this is from the documentation. So we have our processor chain starting with run initialize. Before that, we specifically set to make sure our DAC has digitized set to true. This is not strictly necessary because by default, we're digitizing the waveforms set to true. Then we run our DAC simulation. Here we're running split EV DAC with a trigger threshold of 5 PMT hits. We then run the waveform prep processor. That does all of the, like I said, the simple processing of the waveform. And then there are several different higher level waveform analysis processors that you can run that will produce information by basically fitting or interpolating the PMT pulses to extract more precisely things like the arrival time of the photoelectron. So this includes waveform analysis log normal, which fits a log normal distribution to the PMT pulses, waveform analysis Gaussian, which fits a Gaussian distribution to the PMT pulses, and this waveform analysis sync, which does an interpolation between the samples, more precise interpolation between the samples in order to extract hit times. Okay, I think I'm about to give a summary of what I just said, which I know is a lot of information. So yeah.
I had a really quick question. So if you don't, so by default digitize is true, but if you don't set those like 3 commands, does it assume that you do it, or like what happens if you set digitize to true but don't do those 3 commands at the bottom?
Okay, so the digitize being true here only impacts split EV DAC.
Okay.
So if you don't run a DAC, none of these waveform analysis things will work there because you're not actually digitizing the waveforms. I don't know if rat crashes or just gracefully tells you like, or just skips. I think it just skips the empty waveforms. It won't do anything. So you have to run this DAC for any of this waveform processing to work. And if you do not run any of these processors, you won't produce that information. So let's say you left off all the waveform processing, all these waveform processors, you won't fill the digit PMT object with any information. These are the things that are filling the digit PMT object. They will not run by default. They need to be specifically called in the macro. That's similarly for the DAC. If you just don't run the DAC processor, you're not going to get anything downstream of the truth information. Okay, this is a summary of a lot of things that we've talked about, and then I'm going to go into a couple more processors and then how to write a processor, and then I'll be done. Okay, so we started today with generators creating particles that then interact in materials. We moved on to how the photons are created and propagated through the detector and how they're detected by PMTs. And then based on the true number of photoelectrons, the detected light, we can ask RAT to issue a trigger done through the DAC simulation. That's what I just talked about. Based on the trigger, we optionally digitize the PMT waveforms. And if we choose to digitize the PMT waveforms, we can also run the waveform analysis code. This waveform analysis code fills this information into the digit PMT object. And then your fitter typically interacts with information from a digit PMT. So then that fitter produces your reconstructed quantities, as Sam will talk about tomorrow. But that's sort of the full chain about how to go from generating the particles to reconstructing the particles. Okay, so a couple other processors just to go through just to get to all of them. The prune processor is pretty simple. The idea is that you can actually remove parts of the data structure from your output file just to save space. I won't go into too much detail on this one. The commands are there, it's documented pretty well. And there's basically you provided a cut list and you can set a variety of different names to cut. So you can cut, for example, all of the MC particles out of your branch if you're worried that that's going to be some huge, enormous part of the branch that's going to occupy so much this space. This does not run very often, but it can be useful. I mentioned the output processors a bunch of times. These write the data to disk. You have two options. One is the out n tuple format, and as we mentioned before, that's a flat root tree, T tree, and those are fairly easy to work with. I'd recommend almost always using those. There's also the out root format. I think most of the example files have this ratproc out root instead of out n tuple, and that's something we should change because out n tuple is far more popular choice, I would say. And the details of this are subject to Tony's talk tomorrow, and we'll also talk about actually analyzing the output files in more detail. And then again, the reconstruction processors, the things that take the PMT timing and charge and hit pattern information and turn that into estimated quantities about the physics events, is the subject of Sam's talk tomorrow. Those are also implemented as processors. Okay, and then here's a full example of a processing chain and what it might look like. So this is something we can provide. There's no example macro that includes all of these commands. I think they're all included in at least one, but they're not all together anywhere. So we should just put something more together like this. So again, a full processor chain, which starts with run initialize. You enable the PMT dark noise. You run some data acquisition. So this could be the force trigger or the split EV DAC. You run you want to ensure that the digitization is turned on, which it is by default. You run your waveform analysis, which you can include all four of these. They'll all produce information written to the digit PMTs separately. Nothing will get overwritten, so you can run them all together. Then after you run your waveform analysis, you run your fitters. So RAT, as Sam will talk about tomorrow, provides several example fitters, none of which are particularly sophisticated, but some of which may be useful. So a centroid fitter and a quad fitter that Sam will talk about tomorrow run to extract information from the waveform analysis to estimate quantities about the event. You can optionally run the count processor, which I think is almost always a good idea to run just to give you a useful diagnostic while you're simulating events. And then you finally write out the file to some format. I would always recommend using, and I have a typo here, out n tuple. Okay, and last is the Python processor, which I have not talked about because it's relatively unsupported. We started playing around with it recently and it seems to work fine. It's documented a little bit now, so I would just refer to the documentation in most cases. You can actually write processors in Python rather than C++. And so if you really prefer Python and really need to write a processor, you're welcome to play around with this. There's an example called count.py that is exactly the same thing as the C++ version of the count processor. You call it a little bit differently from the macro. I'm putting the documentation there. So yeah, you're more than welcome to write processors in Python and they should work, but they might require a bit of hacking. This has not been relatively supported feature of RAT, but should work. Okay, so last part of my talk is creating a new processor. I'll try and get through this part very quickly. All of the RAT processors inherit from the processor class. So there's a class in RAT called processor, and they all inherit from that. So I would always use the count processor as an example for how to start. If you're going to write a new processor, start with a count processor and just start renaming things. all processors inherit a set of methods from the processor class that are fairly straightforward to use. There are these set methods, set I, set D, set F, etc. These are what the proc set command are using. So let's say you wanted to allow the user to change a variable in your processor. These set I, set D, etc. allow the user to change a variable in your processor, and the ID, etc. refer to different types, integer, double, etc. And then I'm going to go through each of these different methods. So in your processor, you really only need to include these methods: begin of run, end of run, and either DS event or event. And I'm going to go through all of those in just a little bit of detail. As I just mentioned, yeah, the set methods are pretty straightforward. Again, you can see from the count processor a very specific example. It allows you to change a parameter in your processor. It allows the user to change a parameter in your processor using ratpac-two. And I won't go into too much more detail, because if you want to play around with it, just look at the count processor code. Begin of run is useful. This is where you read the database parameters in the processor. You can set up variables for your processor, etc., and initialize them, etc. This is run one time at the beginning of the simulation. Similarly, end of run allows you to clear memory, close files, etc. Is run one time at the end of the simulation after all the events have been processed. Then there's either, I mentioned this at the beginning of my talk, that you need to be careful about whether you want to loop over simulated events or triggered events. So there are two methods for looping over events. One is called DS event, the other is called event. The DS event method is to loop through events prior to the event branch being created in principle. So all of the DAC processors, which are the things that create the event branch, would use DS event, because you don't actually have the EV branch yet. So you would always use DS event to loop over events before the EV branch is created. The event branch is a convenient method. It's not necessary. You can always use the DS event, but it automatically will loop over the detector triggered events. And so you don't need to worry about looping over the triggered events. That will automatically be accomplished by the event method. So one example where you would typically use that is in your fitter. You want to fit all of the triggered events rather than just the simulated events. So in the fitter, by overloading the event class, you would accomplish this without needing to worry about it. That just is done automatically. The distinction makes sense? That's clear.
So I think this is what you said, but you could just reproduce event by calling DS event and adding an if triggered.
Yes, exactly. Yeah, basically. Yeah, so you can see the bit of code in the processor class that does it, and just copy that bit of code into your own processor, and that would be fine. It's just sort of a convenient thing. Yeah. Okay, and then I'm going to give very quickly you can go through and look at some examples. I think the noise processor is also a good example to look at. So here we're again using the constructor and the begin of run to load some database files, set up and initialize some variables. We go through these pretty quickly because I think probably getting kind of clear. Again, from the noise processor, we use both set I and set D to allow the user to set both integer values and double values using the ratpac set. And there's a bunch of different variables the noise processor is allowing the user to set using these methods. Then the noise processor uses the DS event to loop over events because you haven't triggered yet. You're creating photoelectrons in the PMTs that may actually affect the trigger. And so we're looping over events using the DS event method. And at the end, we return this thing called processor OK. That's not too fun. Okay, and the last thing you need to do is once you write a processor, you need to go to something called the proc block manager that manages all the processors. It's very simple. You'll just see some lines of code that you need to add there to append the processor to the list that Rat knows about and update the CMake list so things compile. Again, a lot of what I just talked about relating to building a processor is actually documented in the programmer guide. One of the only things in the programmer guide that's actually up to date. So writing a processor should be fairly well documented. Okay, and I think, yeah, that's it. I would just say, processes are useful for looping over events, and there should be useful examples for getting started writing one. Okay, cool. Any questions? Great. I will share the list of workshop ideas during lunch, although it seemed like most people were kind of working on their own thing yesterday, but I'll share them anyway in case that was helpful for anyone. So, yeah, cool. I think, we're at lunch